Welcome to Intro to Digital Circuits. Let's start with a quick introduction to binary number systems. In a binary number system, unlike the decimal number system we use on a daily basis, numbers can really only be 1 or 0. This has some pretty serious implications in terms of digital circuits, and is quite important to know. Let's start by getting into what each of the numbers mean. 0, in terms of a binary system in digital circuits, means that the switch is off or there is no voltage. Conversely, I'm sure as most of you guessed, 1 means on, implying that there is voltage present in the circuit and that pretty much it's going to be on. With our knowledge of binary systems at hand, let's get into our first logic gate, the AND gate. Logic gates in practice are made up of a network of transistors which pretty much make up the function of the gate. On the screen here is a schematic, truth table, and Boolean algebra representation of the AND gate. Let's start with the schematic. The schematic has two inputs, x1 and x2, which result in an output, f of x1 and x2, which just sort of refers to it as a function. It doesn't really matter what you call the output. You can call it y, z, or any real variable. And to the right of the screen, you can see the truth table. Now, the truth table has the corresponding inputs and outputs of what the logic gate actually does. This is pretty important, as it shows us all the possible functions of the AND gate. Some examples would be if x1 is 0 and x2 is 0, f of x1 and x2 would be 0. As a matter of fact, the only time when the output is actually on is when both of the inputs are on, which is sort of what the function of the AND gate does. This is very important, as the AND gate is a very important building block for the rest of digital circuits. Finally, we have our Boolean algebra representation. The Boolean algebra representation of all the logic gates are quite important, as they allow us to show complicated structures like truth tables and schematics in very simple algebraic form. Now, with this knowledge at hand, let's sort of get into how this would sort of function while we're doing a digital circuits problem. Let's say our x1 signal, which is a binary signal, meaning it can only be 0 or 1, equals 0. And let's say that our x2 symbol is 1, meaning that it's on. So our x1 signal is off and our x2 signal is on. These two signals being inputted into the AND gate get us the following result. So x1 is 0, x2 is 1, and we do 1 times 0 as shown by the Boolean algebra, and I'm sure as many of you could have guessed, our output is 0. Now, let's see if our truth table has the same corresponding result. And looking at our truth table, taking a look at specifically the second line, x1 is 0, x2 is 1, and f of x1 and x2 is 0. This is a pretty nice result. Our truth table corresponds to what our outputs would be. Let's give another example of Boolean algebra where x1 and x2 are both 1, meaning they're both on. Now, I'm sure as many of you could have guessed once again, 1 times 1 equals 1 as shown by our truth table, meaning that the results in our truth table directly correspond to what we would get in terms of Boolean algebra. And this is sort of how to analyze a gate and how to sort of see what it does. And this specifically is the AND gate. All right, now that we know what the AND gate does, let's get into our second gate, the OR gate. The OR gate is the second most important gate in all of digital circuits, but really there's no point of ranking them. They're all equally important. So, drawing the schematic of the AND gate here, this is sort of what it looks like. It's similar to the AND gate, but it's a bit more curvy and pointy, which is pretty cool. It has two inputs once again, x1 and x2, and it also has an output, z. You guys know the drill. Let's draw the truth table. As you can imagine, it functions similarly to an AND gate, but it has slightly different outputs based on the inputs given. Once again, the OR gate takes in two inputs, which I've called x1 and x2, and an output, z. Similarly to the AND gate, the OR gate returns 0 when its two inputs are 0. But what's different is that when either one of the inputs for the OR gate is 1, the output will also be 1. Similarly, when both inputs are 1, you can expect an output of 1. Finally, let's get into the Boolean algebra representation of the OR gate. So z equals x1 plus x2. That's right, an OR gate kind of functions like addition, which makes sense. 1 plus 0 is 1, 0 plus 1 is 1, and 1 plus 1 In this case is sort of the weird one, which equals 1. But like I said, in binary systems, unlike decimal systems, we don't go past 1. So 1's really the maximum number you can get. I mean, you can't get more on than on. So a quick example, x1 equals 1 and x2 equals 0. Z equals 1 plus 0, which means z equals 1. I'm sure as many of you have guessed. Confirming this with the second line of our truth table, we can see that x1 is 1, x2 is 0, and our corresponding output z is 1. This is why truth tables are so important. It's a really quick lookup of exactly what your function returns. Now that we know the AND gate and the OR gate, we can get into our third and final gate for this video and show how we can compose different logical functions from them. Alright, let's get into our third and final gate for the video, the NOT gate. The NOT gate is a pretty simple one. It really only has one input, and once again, I will be calling the input x1, and it has one output, which once again, I will be calling z. The NOT gate kind of looks like a triangle with a little circle at the end. I think it's a very cool one. It's very unique in that it's one of the only ones that really has one input, and you'll shortly see why. Drawing the truth table for the NOT gate, we have a nice and tiny one this time. We see that when an input is 1, the NOT gate reverses it and gives us 0. And when an input is 0, the NOT gate once again reverses it and gives us 1. In Boolean algebra, NOT gates are represented as either x1 complement, so variable complement, or x1 prime, or variable prime. Now that we know what all the logic gates do, let's get into an example. Joe's an engineer at Circuit City. He is asked to find the algebraic representation and truth table for the following schematic, but clearly Joe is not very diligent when learning digital circuits because he needs your help. So, analyzing the schematic below, let's first take a look at this OR gate here. It takes in the inputs x1 and x2. We know from what we learned from Boolean algebra that this really just means x1 plus x2. Now let's direct our attention to the other input on the schematic, which is x3. x3 just goes through a NOT gate. And as we learned previously, we can represent this as x3 complement or x3 prime. I'm going to represent it as x3 prime because I feel like it. Finally, we have our AND gate. And our AND gate takes in the output of our NOT gate and the output of our OR gate, meaning that we need to multiply x1 plus x2 with x3 prime. And that's what gets us z. Now, you guys gotta admit, that's pretty neat. Just with these silly pictures, we were able to gather an equation which gets us some sort of logical meaning. That's pretty amazing. And with these equations, we can create a truth table, so people who just see this sort of schematic can, find out what it does and can be like, oh, well, these inputs get us these outputs. And you gotta admit, that's super neat. So I'm just drawing a truth table over here, and I'm putting in all the inputs, x1, x2, and x3, and z. Now, we want to know what it does for every possible input. So since we have 3 variables, this truth table is going to be particularly large in that it's going to actually have exactly 8 lines. So I'm just drawing the truth table here. One thing to consider is that with the equation at hand, it's going to be very easy to find results for our truth table. And you guys will see that quite shortly. So, drawing the final lines. And 1, 1, 1. So, let's take a look. I'm going to do a few examples for you, and I'm going to leave the rest of the truth table for you guys to finish by yourselves. What we're trying to find right now is z. So let's start with the first line. Z equals 0 plus 0 times 0 complement. So 0 plus 0 will obviously be 0, and the opposite of 0 is 1, so we get 0 times 1, and normal algebra tells us that 0 times 1 is 0. So z, for the first line, where all 3 inputs are 0, will be 0. Now, let's do the second line. The second line, I'm sure as many of you can guess, will have a similar output because x1 plus x2 is once again 0, and anything multiplied by 0 really does get you 0 again. So this one, whoops, not x3, we want 1 complement, which will also be 0. So we get 0 times 0, and I'm sure as many of you can guess, our output is going to be 0. And so the first two lines in our truth table get us 0. So this is a bit of a slower process, but it is quite important. So moving on to our third line, we get that x1 is 0 and x2 is 1 times 0 complement. Now 0 plus 1 is obviously 1, which is nice, and 0 complement is 1, which means that we finally get an output of 1, or on. Now, I'm going to leave the rest of the truth table as an exercise to you, and hopefully you learned something new. See ya!